Welcome to Programs Forecast number 80, and today we're looking at sharper turning drones using avian-inspired wing and tail morphing. So regular drones, they often are just fixed wing, but now we're looking at drones with wings that can change shape and orientation, and their tails as well. And this is using avian-inspired wings and tails. So to do that, we're going to be looking at a paper. It's open access again. You can find it in the link in the description. It's called Sharp Turning Maneuvers with Avian-Inspired Wing and Tail Morphing. So let's get into it. First of all, actually, I should mention that the turning that we're looking into is roll. So if you think about, if you put your hand out in front of you and the palm is facing down, and then you wiggle it from left to right, that is yaw. Then if you rotate it so the palm sort of faces up a little bit and then down and up and down, that's roll. So we're going to look at the roll section instead of the yaw or the pitch. The pitch is if you were to move it in the third direction. So let's focus just on the roll right now, and then in other podcasts, we might look at other turning aspects such as yawing and pitching. So let's get into it. So multicopters are often used to fly in dense environments such as cities because they display higher agility, albeit at the cost of substantially low flight endurance compared to fixed-wing drones of similar mass. Fixed-wing drones, instead, are used in missions that require high endurance and range, such as surveys of agricultural mapping. And this is very normal. Like if you think about a helicopter compared to a fixed-wing aircraft like an airplane, we all know that helicopters are very maneuverable. They can hover in space and they can land vertically and take off, whereas airplanes usually don't have any of those abilities. But the benefit of airplanes is that they can travel much further distances and usually much faster. So that's a similarity between these multicopters and regular drones. So they say, however, these fixed-wing aircraft need a comparatively large space to turn and thus only fly in open spaces. Here, they show that an avian-inspired folding and pitching wing system substantially improves the turning capability of fixed-wing drones with propeller-driven thrust. So that's very good because, as we know, helicopters, they can sort of just turn right on the spot, whereas airplanes, they need to bank around to be able to turn. We've all been in an airplane and we know what that feels like. So a turning maneuver can be separated into two phases. The first phase is a roll phase, and the second phase is a banking phase. So during the roll phase, drones increase their bank angle by applying a rolling moment. So let's talk about this quickly just to break it down. So let's say you have an airplane in steady flight. To turn, it first has to roll about that axis that I was talking about, the x-axis. That's roll, and then it starts to bank, which means that it's you see it turning on its side almost. That's banking. They say the roll performance is best when the time to reach a desired bank angle is minimized. Once the desired bank angle is reached, the bank phase begins. When banking, the lift vector is composed of a vertical and horizontal component. So this is important because typically we just think of lift as being directly straight up. However, that's not exactly the case in terms of banking, because now the lift force, which is perpendicular, which is straight up from the aircraft, is now at an angle to the ground and gravity, because the aircraft is now at an angle to these two surfaces or these two directions. So that means that the lift force, if you were to break it down into the vertical and the horizontal directions, there's a component in each direction now. So again, the lift force will have some part of its force actually going straight up into in respect to the Earth, but there's also going to be a part horizontal with respect to the Earth. The airplane, however, it doesn't understand any of this. It's just a lift force which is always perpendicular to the wing surface. So they say the vertical lift force component must be equal to the drone's weight force to maintain altitude, while the horizontal lift component creates the centripetal force that causes a turning motion. So what that means is if you want to keep your airplane at the same altitude, even though the lift force now is at an angle to the ground, the component that is in the direction of the of gravity has to be equal and opposite to the force that gravity is exerting on the airplane in order to maintain a level flight. So that means you have more lift being produced now. Otherwise, you'll start to reduce your altitude. So the bank phase performance is best when the turn radius is minimized, which requires lift to be maximized. That is because the greater the lift, the more centripetal force there is, and then the faster you can turn around. Thus, the overall performance is maximized when both the roll time is minimized and the lift vector is maximized. So conventional Drones initiate the roll phase with ailerons, which are flaps on the trailing edge of the wings that are deflected in the opposite direction to each other. So what this means is if you've been on an airplane, just when you look out the window onto the wing, there are some at the back of the wings, the trailing edges, there are all these like little surfaces that can move up and down. And if you look at the wings in pre-flight when they're doing their tests, you can sit on the airplane like inside and you can just watch them do that. And you see these little flaps going up and down just to make sure that they're working. So the ones inboard, very close to the or closest to the windows, those ones are mainly used to increase the lift of the wings in a symmetrical fashion. So both the flaps on the left and right wings will be deployed at the same angle typically. But then the ones further out near the wing tips, these ones are called ailerons, and these ones will be pitched at different angles of attack to change the resulting lift of each wing individually. And the reason why that is because lowering the aileron increases lift, whereas raising the aileron decreases lift. The reason why is because if you lower the aileron, it means that the wing effectively has a greater angle of attack and also more camber. Both of these things result in higher lift. And if you flip the angle of attack of the aileron the other way, the opposite occurs. So the force asymmetry between the two wings, resulting from this asymmetry of the aileron deflections, causes a rolling moment, which translates into a roll motion. Ailerons are widely applied to today's winged drones because of their simple mechanical design and aerodynamic efficiency. During the bank phase, winged drones usually maintain a constant bank angle until the desired heading is reached. To improve the turn performance when banking, drones deflect the tail elevators upwards, which increases the wing's angle of attack and thus the overall lift to reduce the turning radius. So let's talk about this and how this works. So if you have a regular airplane, the horizontal stabilizer, which is the horizontal part of the tail at the back, that is typically used to control the pitch of the aircraft, at least to a large extent. Why that is because if you think about where the aircraft is pitching about, so that means whether the nose is going up or down, pitching. If you have the horizontal stabilizers at the back, so the tail, producing lift, so it's positive lift, that's going to make the airplane pitch downwards. So the nose is going to go down because you have a force behind the point at which it's rotating, the axis which is rotating. If you put the horizontal stabilizer at an angle, particularly the aileron at the back or the flap, so that it's producing negative lift, it means that you're pushing the back down of the aircraft, which means that the nose is going to go up. So this is how you can increase the angle attack of the entire aircraft and of the wings through the tail. If you create a downforce, so negative lift at the back, that's going to pitch the entire aircraft up at an angle of attack. The wings are going to stay at the same relative angle of attack compared to the entire aircraft, but because the entire aircraft is pitching up together with the wings, the global angle of attack of the wings suddenly increases. So now that's how you can increase the lift that it's producing. Now, obviously, you get to a point where you will reach stall, and that's a problem. But up until that point, you will be doing much better. So let's look at figure 1 here. So gliding birds. So we have figure 1. If you're watching this on YouTube, that's great. If you're listening to this on a podcast, note we do have the video on YouTube. So if you want to watch the video as well, you can go on YouTube and find that. So in figure 1, we have 6 different figures showing aircraft in different flying maneuvers and also birds. So gliding birds can perform sharp course variations that outperform current winged drones. They do this by modifying the shape and inclination of their wings and tail. So for rolling, birds can resort to 2 strategies. The first is asymmetric wing folding and wing twist. Wing folding is predominantly achieved by flexing the wrists and results in a reduction in the wing area. The lift force produced by each wing side is linearly dependent on the wing area. So we know that lift equals half times density times velocity squared times the surface area times the lift coefficient. So you change that surface area, changes the lift linearly. Obviously, the lift coefficient does change as well, but assuming that it stays a constant, then it changes linearly. So folding only one side of the wing produces an asymmetric lift distribution along the wingspan that results in a roll motion. This is because one wing now has a smaller surface area, so it has less lift being produced than the other wing. So that means that you're going to roll in that direction. Furthermore, reducing the wingspan lowers the flight inertia and enables the bird to reach the desired bank angle faster. So let's briefly talk about this. So the inertia is referring to how much, first of all, how much mass there is, but also where that mass is distributed around the bird or any object. The further the mass is away from the center, the point at which it rotates about, the harder it is to rotate that object. So if you can bring a wing in closer, so you tuck it in, that means that you're bringing a lot more mass closer to the axis in which the bird will rotate about. That means that it's easier to turn, which means you don't need to have as much force to do that. So it means it can turn quicker. So that's quite good. So that's the first strategy in um, which a bird can bank or roll. It just tucks one wing in and keeps the other wing straight. The second strategy consists in actively twisting the wings that it changes the incidence angle of each wing side, which is achieved by pronating or supinating the wrists. So this is akin to the typical way that we roll our aircraft, which is you change the aileron deflections. So increasing the wing incidence angle, so pronating increases the lift, whereas decreasing the wing incidence angle, so supinating, decreases the lift. Pronating one wrist and supinating the other generates an asymmetric lift distribution along the wing span, resulting in a rolling motion. So birds may use both of these strategies, wing folding and wing twisting, independently or in combination, and that will achieve rapid roll. However, the aerodynamic impact of wing twisting and folding when turning in gliding birds is not fully understood yet. So they say that avian inspired. So let's continue with this figure. So once the bank angle is reached, birds can benefit from symmetric wing and tail morphing in order to reduce the turning radius. So they not only change the wing span, but also the tail. They can extend it or fan it out a bit more. And we also see this all the time. If you look at a pigeon landing, you'll almost always see the tail really fan out a lot as it's coming down to land. So extending the wing and tail leads to an increase in aerial surface and thus lift. Furthermore, sweeping the wing forward and enlarging the tail results in a higher angle attack, which results in an overall increase in lift. The lift increase from wing and tail morphing allows birds to fly at high angles of attack and thus reducing their radius. So we're going to cover how the tail does this a little bit more later, but just briefly, I'm going to say that the tail, they pitch it down a little bit. And the reason why this increases the lift is because you have to now think of the bird as an entire lifting surface. So if you pitch the tail down, you're effectively increasing the camber of the wing, which the entire bird is like one big wing now. A bit of a funky looking wing, but it's a wing nonetheless. And so this is going to naturally increase the lift. So we're going to cover that a bit later, but I just wanted to do that now just to make sure I remember. So avian-inspired asymmetric wing folding or asymmetric wing twisting, so either when they tuck the wing in or they twist each wing individually, have recently been applied to winged drones and tested in flight. It has been shown that asymmetric wing folding can be used to control roll or to maintain a steady bank angle. In the researchers' previous study, with an avian-inspired drone capable of morphing both the wing and tail, they noticed that rolling by asymmetric folding of the wings must be preceded by a slight increase of angle attack of the drone in order to produce a turning behavior. So in other words, when they are tucking one wing in, they need to roll. They need to also precede this by a slight increase in lift. So this insight led them to suspect that the drone could have profited from the ability to slightly twist the wings as birds do. However, to date, the influence of wing folding and wing twisting and tail folding on turning performance drones and birds remain largely unknown. So this is where this research comes into it now. Here, they systematically assess the relative impact of wing folding and wing twisting on rolling performance, as well as the impact of symmetric wing and tail extensions to increase lift and reduce turning angle during the banking phase for rapid turning maneuvers. By including the ability to individually pitch the two sides of the wings, similar to birds, that's how they're going to do it. So to estimate how asymmetric folding and pitching compare due to the rolling phase, they conducted wind tunnel tests to measure the roll moment and also performed roll flight testing. They showed that the asymmetric wing pitching leads to notably larger roll moments than asymmetric wing folding in cruise flight, leading to higher roll rates that enable the drone to reach the desired bank angle faster. And we're going to cover that later on as well. So let's move into the results now. So in figure 2, they have a bunch of pictures. They have a picture of their really cool machine. It looks very bird-like. So it has a tail, and then the main part of the bird is it looks like just a plastic structure, but then at the back, at the wing tips, they have these feathers now. So that's really cool. It's almost bird-like. So this avian-inspired drone, they developed this drone with feathers at the back, and they called this the Lys Eagle, which builds upon a previous prototype with a feathered morphing wing and tail. The drone has a maximum wingspan of 1.52 meters, so it's really big, and a ready-to-fly mass of 711 grams. Now, I thought this was really amazing considering that it's less than a kilo, but it's like 5 foot in span. But they say a little bit later on that this is fairly normal for birds this big. I don't know, maybe like a condor or something. I thought they were a bit heavier, but maybe there are other birds that fit into this weight and size bracket. So either way, it's really cool to get something so big but so light. Like birds, their Liz Eagle drone can independently change the sweeping angle of the outer wing sections made of artificial feathers. So changing the sweep angle allows the drone to change the wing area and shape in flight. They have a picture here of how they do this. So the wing tip section, so like the last third of the wingspan, they can actually sweep this part itself backwards or forwards. When they sweep it backwards, it reduces the surface area of the wing by, they mentioned later, about 31%. And if they sweep it forwards, it increases the area, surface area there. And they can do each one individually as well. So further, also the drone can independently change the incidence angle of each wing side, equal variation of incidence angle along the entire length of the wing, and they call that wing pitching. Furthermore, the Lys Eagle possesses a morphing tail made from artificial feathers that can change its area by fanning in and out and deflect in the XZ plane, analogous to the elevator of a conventional aircraft. So that's the tail section. To roll, the Lys Eagle either folds or pitches its wings asymmetrically. When folding, one wing side is extended by a maximum of 85 degrees. So that's where I mentioned that it sweeps it forward, that end wingtip bit, and the other side remains tucked, resulting in a larger lifting surface on the side of the wing that has been swept forward. Since this is proportional to the lifting surface area, the extended wing side produces more lift than the tucked wing side, which causes a roll motion because there's more force on one side pushing that side up over. When pitching, so they say about plus or minus 10 degrees, so this means the wings are pitching at a high angle attack or low angle attack. The incidence angle of one wing is increased while the other is decreased. The resulting difference in angles of attack between both wing sides, a maximum of 20 degrees, the difference, causes a roll motion. So this is akin to how we roll in our airplanes these days, where you just change angles of attack effectively. And a maximum of 20 degrees change, so minus 10 degrees on one side, plus 10 degrees on the other side, is quite a lot. If you look at a lift curve slope of an airfoil, a typical airfoil for flight, that corresponds to like lift coefficient difference of like 1.5 to 2. Depending on the airfoil. So that's a massive difference. To increase the lift during the turn, the Lys Eagle can apply two avian-inspired morphing strategies. As we mentioned, when we're turning to maintain a level flight, we need to increase the amount of lift we're producing because some of that lift is now in the horizontal direction instead of the complete vertical direction. So to do this, they can either have tail elevation or wing and tail extension. So in other words, you move the tail up or down, or you extend the wings and tail surfaces. The tail can be continuously deflected between a range of minus 30 degrees, so 30 degrees upwards, or 15 degrees, so 15 degrees downwards. So a 45-degree range. The tail elevation produces a positive pitching moment, which increases the drone's angle of attack and thus lift force. So as I mentioned, with regular airplanes as well, by pitching the elevator down, you're producing a lift up, which then pitches the nose forward, and that reduces the angle of attack of the entire aircraft, and vice versa. Extending both wing sides by 85 degrees and the tail by 120 degrees leads to a total area increase of 41% for the entire bird, and a large positive pitching moment. The combination of tail deflection and wing and tail extensions enable the drone to fly a high angle attack while generating large lift forces. So that's how their bird operates. Let's move on to the rolling phase now, because this is what we're interested in, how this bird with this mechanical bird can achieve greater roll. So the rolling phase, figure 3. In figure 3, we have the bird at different, I should stop calling it a bird, the Liz eagle has different wing geometries, and they have their rolling moment coefficients plotted. So they say initiating a rapid turn maneuver requires a fast transition from cruising, so tucked wing and tail configurations at 0 bank angle, to the desired bank angle for the banking turn. The only external variable affecting the roll motion is the aerodynamic roll moment induced by the modifications of the aerodynamic surfaces. So in other words, the only way to actually roll is to change your surface orientations and sizes to initiate this. To decrease the time to reach the desired bank angle, which is beneficial, we want that, and thus improve the roll performance, it is necessary to produce a large rolling moment. To estimate the roll performance of asymmetric wing folding and pitching, they compared the roll moment coefficients of the two drone configurations. Either the first one is with the extended left wing while keeping the right wing tucked and without applying any wing pitching. And the second one is you keep the wings at the same tucked position, but you pitch the left wing downward by 10 degrees and the right wing upward by 10 degrees while keeping both wings tucked, as I mentioned. So they obtained the roll coefficients through wind tunnel measurements, and they performed an angle attack between -8 degrees and 20 degrees in 4-degree steps at an airspeed of 10 meters per second. So the experimental results revealed that asymmetric wing folding generates a low roll coefficient of only 0.016 during cruising flight. So this is between 2 degrees and 8-degree angle attacks. Although the roll coefficient steadily rises with increasing angle attack. In comparison, pitching the two tucked wings generates a substantially larger roll moment coefficient of 0.079 in cruising flight, although it rapidly decreases with increased angle attack. So let's talk about this, because this is a really, really important and juicy part here. I'm going to zoom into this figure here. So what they're saying is when you rely on just changing the wing surface area to create the rolling motion, this at low angle attack, so cruising angle attacks, this is a very inefficient way of doing it. So let's talk about why this is, relatively speaking, at least. So I mentioned earlier, if you were to, when they swept the wing tips forward, so one wing tip went forward, one wing tip stayed at the same tucked position, the difference in surface area is now 31%. So that means that you're going to get a 31% increase in the lift coefficient. So that's a pretty decent amount. However, compared to rotating the wings, so pitching them up and down, that's not very much at all. If you look at pitching the wings up and down, so let's say you have your wings now at, let's say, 4-degree pitching angle attack. Now, angle attack right there. Now, they say that they can pitch one wing up 10 degrees from there and the other wing down 10 degrees from there. So that's a massive difference. As I mentioned, that's 20-degree difference. That's going to result in a difference in lift coefficient of 1.5 or 2. So if you were to calculate that in terms of percentage, if you're at 4 degrees angle attack and you're cruising along, this coefficient might be about 0.4. If you were to pitch one wing up at 10 degrees, you're going to now be about 1.4. So that's, what's that, a 2 times increase, a bit more than that, 2.5 times increase. The other one, you pitch down by 10 degrees, that's a 2.5 times decrease. So it's 20% on one side, 20% on the other side in the opposite direction. So that's a massive change in the lift coefficient. Compared to sweeping the wingtips forward at 4 degrees, let's say, you're only going to be producing an extra 30% on one side. So it's not very much. That makes sense geometrically and physically why pitching the wings instead of sweeping the wings will give you a much greater roll motion. Now, this is at low angle attack, remember. Now, high angle attack, it's not actually the same setup. So it's not actually the same results. So at low angle attack, pitching the wings up and down is far more effective at rolling, but at high angle attack, so above here, they have 10 degrees is the point at which this trend changes. So at 10 degrees, once you go above that, sweeping the wings forward, and keeping the other one tucked, is much more effective than pitching the wings. And I think you can probably figure out why that is. And the reason why is because if you are now pitching the wings up and down and you're, let's say, 20 degrees or even 15-degree angle attacks, increasing angle attack by 10 degrees is really asking too much of most airfoils. Like they're going to stall most airfoils. Now, the other airfoil, you can drop that angle attack by 10 degrees and you're going to be fine. You're still going to be well in the attached boundary layer region. But if you have the other wing, which is stalling, you're going to be reducing lift on there anyway. So the amount of roll that you can produce from this maneuver at high angle attack is not very much compared to at low angle attack, at least. This is where sweeping the wing, one wing tip forward and keeping the other one tucked is going to be more effective, because you can sweep this wing tip forward and you're still going to be producing lift because you're not really changing the angle of attack now. So you're now relying on the surface area, and that's not going to change how much the flow is staying attached or separated. So that's why at high angle attack, this ability to sweep the wingtip forward is much more effective at rolling than to pitch the wings. But then at low angle attack, pitching the wings is far more effective. Okay, so let's move on from here. So let's talk about the banking phase now. We talked about the rolling phase, which is when we are trying to initiate the banking, which is the prelude to it. Let's talk about the banking phase now. So figure 4 is just the banking performance for 3 different wing and tail configurations. Let's talk about each one of these ones now. I'll zoom out a little bit so you can see the legend and the axes. Okay. So turning with a small radius requires large lift forces, as we've mentioned before. To identify how wing and tail morphing can increase lift when banking, they performed wind tunnel tests and measured the lift and pitching moments for different angles of attack in 3 configurations. The first configuration is tucked wing and tail. Second one is tucked wing and extended tail. And the third one is extended tail and extended lift and extended wing, sorry. So all out in this one. While deflecting the tail upwards by 15 degrees for all these maneuvers. By extending it by 15 degrees upwards, means you're producing a downwards force, and that's going to be pitching up the nose a little bit. During a steady banking turn, the drone is in equilibrium and the sum of all forces and moments are 0. Thus, it follows that the pitching moment coefficient must be 0 too. When tucking, if it wasn't 0, then you'd have an imbalance of the forces and you wouldn't have a steady banking phase. It would be either like accelerating into it or decelerating out of it. You can think of it like that way. When tucking wing and tail, while deflecting the tail upwards by 15 degrees, their measurements indicate a pitching equilibrium at an angle attack of 4.5 degrees, leading to a lift coefficient of 0.52. So not bad. However, while maintaining a tucked wing, but extending the tail and deflecting the tail upwards by 15 degrees still, the equilibrium angle rose to 12.5 degrees, thus increasing the lift coefficient to 0.83. Now, when extending the wing and the tail and deflecting the tail upwards by 15 degrees, the pitching equilibrium is now at 38 degrees angle attack, which is huge, and the lift coefficient is now 1.68, so massive. What that means is really extending any of the lifting surfaces is very beneficial in terms of increasing the lift coefficient, which is beneficial for making the bank phase more aggressive and quicker. So they said they can expect a notable reduction in turn radius when extending the width and tail, resulting from the lift increase by a factor of 3.2 compared to having all these surfaces tucked in. So the steady banking turning model that they've developed, they use this to analyze how the aforementioned changes in lift coefficients affects the turning radius. So in other words, it's just a model that they used to develop. They developed so they can understand how these changes in lift coefficient will affect the turning radius. They say the model predicts that for low lift coefficients, so for example, 0.52, as measured for the tucked wing and tucked tail configuration, the drone must perform turns with a radius of 12 meters in order to compensate for the downwards force of its own weight. Increasing the lift coefficient decreases the turn radius. For example, at the maximum, like the best case scenario where they had the wings extended and the tail extended, the lift coefficient was 1.68. And in this configuration, the minimum turn radius is now 4.8 meters, a massive reduction. They say another factor affecting the turn radius is the load factor, which is the maximum expected lift force divided by the drone weight. And this is a very important factor. It can be thought of as really how much, first of all, how much additional lift you're producing compared to how much lift you need for steady flight. The second way of thinking about this is how quickly you can ascend. So the more lift you can produce compared to your weight, the quicker you can go up. So the turn radius decreases with increasing load factor, so increasing lift compared to weight, which makes sense. For example, at a lift coefficient of 1, increase in load factor from 1.5 to 4 decreases the turn radius from 7.6 meters to 5.8 meters, respectively. Now, that's not a huge amount considering that you have a massive increase in the amount of lift you're producing compared to your weight, but it's still a reduction. They say they designed the Liz Eagle wing, so their bird here, the wing and tail, to withstand a load factor of 4. So that's quite high still. So the discussion, let's talk about what they've found in overall. So their study highlights the limitations of the asymmetric wing folding to control roll during cruise flight. So in previous studies, asymmetric wing folding was used successfully to roll, but the angles of attack were not reported in those studies. Their flight tests showed that asymmetric wing folding is not very effective to roll the drone in cruise. And I stress that in cruise because it's important because at high angles of attack, that is the opposite way. This folding wing approach is much more effective than the pitching wing approach. But that's a high angles of attack. During cruise, the pitching wing approach is much better. They say in comparison, asymmetric wing pitching results in 426% higher roll rate compared to the tucking, like the folding way, i.e. reaching a much higher bank angle within a given amount of time. So they say their drone could reach a bank angle of 10 degrees in only 0.4 seconds with asymmetric folding of 60 degrees with asymmetric wing pitching within the same amount of time. So in other words, if you just fold the wings, in 0.4 seconds, you can only bank at 10 degrees. But if you were to pitch the wings instead at low angles of attack, within 0.4 seconds, you can get 60-degree bank angle, which is huge. You can turn much quicker, much tighter. So they noticed that the roll moment for wing pitching decreases with increasing angles of attack, which is a well-known trend also in conventional aircraft with ailerons. This is because at high angles of attack, increasing the wing incidence no longer leads to an increasing lift force, and it may even lead to a decreasing lift force, resulting in a decrease or even reverse of roll moment. That's because you're now stalling one side of your airplane. However, our results show that the wing folding produces an increasing roll moment with increasing angles of attack. This can be explained by the difference in wing area between the two wing sides, which will always produce a lift difference at increasing angles of attack. This finding suggests that asymmetric wing folding leads to higher roll rates at higher angles of attack than symmetric wing pitching. Producing a roll moment often leads to adverse yaw, which is an opposite moment about the aircraft's z-axis or z-axis, and causes slipping whereby the nose of the aircraft no longer points in the direction of travel. So let's talk about this briefly. At the start of this podcast, I talked about yaw, and I didn't go into it too much, but if you were to stick your hand out and the palm of your hand is facing downwards and the fingers are facing forwards, if you then rotate your hand left to right, that's yaw. And in most aircraft, particularly fixed wing aircraft, you get what's called inertial coupling. This means that when you change the aircraft's direction in one way, another orthogonal direction is going to be changed as well. So if you were to roll your aircraft in this particular case, yaw is also going to occur. So the aircraft is now going to rotate about another axis. And this results in what's called side slipping. So this slipping result is a result of centripetal force and an increased drag that decreases turn performance. Their wind tunnel measurements and flight tests indicate a similar adverse yaw moment and motion, respectively, with asymmetric wing folding and pitching in cruise flight. However, while their wind tunnel measurements indicate an increase in adverse yaw moment and with asymmetric wing pitching at high angles of attack, the adverse yaw moment remains nearly constant with asymmetric wing folding at increasing angles of attack. This finding leads to the hypothesis that asymmetric wing folding might be more favorable in rolling at high angles of attack to minimize adverse yaw effects. So it's more predictable and more stable, in other words, when you're at high angles of attack and you're rolling. It is not yet fully understood why birds use asymmetric folding and twisting to initiate rolling in gliding flight. Their roll phase results in, with the Liz Eagle drone, may explain when birds apply wing folding or twist. Analogous to other aforementioned results, they hypothesized that birds may predominantly rely on asymmetric wing twisting to roll increased flight. So in other words, they're going to be pitching their wings up and down when they're at cruising angles to achieve a high rolling moment and a low adverse yaw moment. But when they're at high angle attack, they may revert to tucking one wing in and extending the other wing, as we've been talking about. This is more effective at high angle attack, whereas pitching the wings up and down is more effective at low angle attack. And this also results in a lower adverse yaw moment as well in this regime. So the bank phase flight experiments indicate that symmetric wing and tail morphing can reduce the turn radius by 56.5% from 12.1 meters to 4.9 meters when the wings are completely extended and the tail is extended. The turn radius reduction resulted from the increased lift force generated by the extended wing and tail. So this gives when both the wings and tails are extended completely, you get a lift coefficient of 1.68. When you tuck everything in, it's only 0.52. So that's a huge difference. Overall, the roll and the bank phase results suggest that the synergistic wing and tail morphing substantially improve the drone's capability to perform sharp course variations and reduce the required space. For example, given a bank angle of 50 degrees and a cruise speed of 12 meters per second, a drone pitching its wings would cover 5 meters from the roll initiation until the bank angle was reached, followed by a turn with the extended wings and tail with a radius of 4.9 meters. So in other words, it would only cover 9.9 meters to perform a complete 180-degree turn. In comparison, a drone that folds its wings to roll and keeping its wing and tail tucked during the turn needs 22.9 meters to achieve the bank angle of 50 degrees. And that's not all. It needs an additional 12.1 meters to complete the turn. So to do the entire 180-degree turn from initiating the banking to banking requires 35 meters. It's a lot more compared to the 12 meter, the 9.9 meters if you were to use the other method of rolling. It's a huge difference. So that's the end of this podcast. Make sure to like, subscribe. And if you have any other ideas that you want us to cover on our podcast, let us know. Otherwise, we've got a whole bunch of other ideas that we're going to be doing out over the next few months. And if you do experiments or you do CFD that require experiments to validate it, check out the Atmosphere Hawk. It makes your experiments 2 to 4% more accurate, which makes your CFD even more accurate. And you can find that in the link in the description. And I'll see you in the next podcast. Peace out, amigos.